I think we'll get started. So it's a pleasure to introduce Professor Rebecca Flint as our seminar, the speaker of our first of the condensed matter seminars this semester. Rebecca got her PhD from Rutgers with Piers Coleman in, I believe, 2010, and she was subsequently Simon's postdoc fellow at MIT, and she's been on the faculty at Iowa State University since 2013, and there she currently is an associate professor of physics. Rebecca's interest has been on strongly correlated systems, including Condo systems and frustrated magnets and other settings for exotic physics. And so without further ado, Rebecca, please take it away. I think I'll let everybody read the title.
Okay, well, thank you. It's a pleasure to be here today giving you this talk. And what I want to talk about is some of the work that was originally started with Piers Coleman and Premi Chandra back in 2013, where we proposed the idea that the hidden order in uranium, ruthenium, 2 silicon 2 could be described by a kind of spinorial hybridization, which meant that your heavy Fermi liquid ended up breaking symmetries and occurring via phase transition. I sort of continued to explore this idea and learned a lot about what's possible and how you really can describe the order. And we were motivated in part by the question, well, if it's really a spinorial order, this is something that has been looked at in Bose-Einstein condensation systems, but not really in materials at all. So we wanted to know if there are any signatures of the fact that your order parameter was really a spinor, given that you can't measure the spinor itself directly. And I believe that there are. I don't know that they've been seen, but I will argue that there are definitely signatures that come from the spinorial nature. And then I will also mention briefly, there's another set of materials based on praseodymium that exhibits sort of similar spinorial order, spinorial hybridization, or at least has the possibility for that. And so I'll discuss sort of all of these possibilities in the context of these systems. So I can't see any of you. So if you have questions, I don't know how you usually do it, but feel free to just interrupt me. I would love to answer questions. Okay.
And also maybe put in the chat if you don't want to shout, and I'll make sure that Rebecca gets the chat.
Yeah. Okay. So first I want to acknowledge all the people who've been involved in this work. So as I said, it started with Piers Coleman and Premi Chandra, and I'll show some nonlinear susceptibility data from Art Ramirez's group at UC Santa Cruz. And then I've had 2 graduate students working on this, Milan Korniaka and Guanghua Zhang, and then 2 postdocs, John Van Dyke, who's now at Virginia Tech, and Victor Quito. So we sort of started off looking at uranium, ruthenium, 2 silicon 2, took a detour to really understand the more general problem, and have come back now to try to do a better job on uranium, ruthenium, 2 silicon 2. So here is sort of the fundamental question that underlies hidden order and why people have cared about this for so long. So this material, uranium, ruthenium, 2 silicon 2, was discovered back in the 1980s, and they measured this specific heat curve, and you see 2 clear mean field phase transitions. And if you're familiar with sort of heavy fermion density wave systems, you think, oh, this is probably just going to be an antiquark magnet with a superconductor at low temperatures. And if it's not that, maybe it's something else, but we can should be able to straightforwardly identify the broken symmetry in the order parameter and publish a couple papers and then put the problem away. And that turned out to really not be the case. It's now been more than 30 years, and we still don't know what the order is. And it's extra surprising because if you look at this specific heat curve, you can integrate up the entropy to the hidden order transition and find the entropy of condensation. And you find that it's 1/3 R log 2. So this is a uranium system. Your uranium moments, you expect to have at least R log 2 entropy. So here you expect a large order parameter. And so you should expect that it should be easy to see any moments associated with that order parameter. But there's still been no moments. There's still no obvious order parameter. There's nearly uncountable number of papers that have been published on this material since then, with hundreds of experimental papers and over 30 different theories, which have brought up all kinds of really interesting ideas. And we're still interested in this because if it looks so straightforward and after all of this effort, we still haven't been able to understand it, maybe it means that we're missing something pretty fundamental. And so in order to sort of talk about our proposal, I want to talk about the basic ingredients, where that sort of fundamental novel idea can come from. So this is the magnetic susceptibility of uranium, ruthenium to silicon 2. So you see at high temperatures that you have Ising-like local moments, which are sitting on your uranium sites. This is a metallic system where conduction electrons are coming from the rutheniums and other atoms. And then you see that around somewhere below 100 Kelvin, the susceptibility turns over, and it looks like it's turning into a heavy fermion metal where you're going to get a heavy polysusceptibility. And okay, so this sort of justifies this initial idea of treating this as a heavy fermion metal. But what's interesting is that it's an Ising heavy fermion metal. And in fact, the Ising local moments quench to form an Ising heavy Fermi liquid. So if you look at the G factor of your Fermi surface and you look at normal conduction electrons, you expect an isotropic G factor that looks like this red line and doesn't depend on the angle of the field at all. However, if you measure the Fermi surface magnetization with de Haas van Alphen, you can pull out the G factor, and you find it has this cosine theta dependence on the angle from the C-axis, which suggests that the heavy electrons now are Ising-like. And moreover, you can look at the nonlinear susceptibility, so chi3, and you see that below 100 Kelvin, where you start to develop this heavy Fermi liquid behavior, your nonlinear susceptibility follows this cosine to the 4th theta dependence, which is also exactly what you expect from an Ising susceptibility. So you see this in the nonlinear chi above the hidden order transition, at the hidden order transition where there's a jump, and then below the hidden order transition in this G factor. So this is, okay. So in order to find an Ising heavy Fermi liquid, the sort of most straightforward picture is that your Ising local moments are actually coming from a non-Kramers doublet, which is always in tetragonal symmetry, which is what uranium, ruthenium to silicon 2 has. It's always has a not, it can have, sorry, there is a non-Kramers doublet in tetragonal symmetry that is always Ising-like. And that's sitting with an even number of F electrons. If you have an odd number of F electrons, you have to be very fine-tuned to getting an Ising local moment behavior. So this sort of motivates the idea that we want to look at what's happening when we have a non-Kramers doublet ground state. And there's another set of systems that also sort of exhibit what I'm going to call weird Condo physics, meaning not the conventional picture. And so these are in cubic materials. You can also get a ground state 4F2 doublet that actually has no magnetic moments at all, doesn't have any dipolar moments. Instead, the shape of the electrons in the ground state doublet has these two different shapes. So one is sort of squashed and one is elongated. And these are degenerate due to the very high symmetry of the cubic crystal field. And so this quadrupolar doublet can then similarly undergo the Condo effect. So Dan Cox did a lot of work on this. And there's a set of 1, 2, 20 materials. Here's some of them that Satoru Nakatsuchi and others in Japan have been working on which show indications that not only do they have this ground state doublet, but this doublet has some signatures of Condo effect. And the materials do seem to order at ambient conditions, but under pressure or in field, this quadrupolar order can be suppressed. And then you have the question of what's going to happen on the other side once you've suppressed it. And when you suppress it in field, you end up with this small region of heavy Fermi liquid. So that was sort of the secondary motivation for what we are looking at. So probably many of you are familiar with this, as Chi Miao and Andrei have both worked heavily on what the sort of global Doniac phase diagram looks like for Condo materials. So the fundamental picture is that when we have these kind of heavy fermion materials, the conventional picture is you can form a heavy Fermi liquid where your local moments are quenched to become part of the conduction sea, or your local moments can order independently of the conduction electrons and form an antiferromagnetic phase. And you have a quantum critical point between them that's sometimes screened by superconductivity. And it leads to a rich phase diagram that has many open questions about quantum criticality and superconductivity. And you can further enrich this with frustration. And there's really a lot of interesting questions here. But actually, this phase diagram is really only dealing with Kramer's doublet materials. So these are materials with an odd number of f electrons, so based on cerium or terbium. And what I'm interested in is materials with non-Kramer's doublets that require actually a different phase diagram entirely and have a whole set of new rich physics. So just to explain what I mean by Kramer's and non-Kramer's doublets, when we have f electron materials, the spin orbit coupling is very strong, and so J is the correct quantum number. And these 2J+1 levels are split by crystalline electric fields. And then J itself can be either half integer if you have an odd number of f electrons, or integer if you have an even number of f electrons. And we know that half integer and integer spins have very different behavior under time reversal. So integer spins behave sort of like what we naively expect. They behave like a vector, and you apply time reversal once, and your spin basically points in the opposite direction, and you apply time reversal a second time, and you get back to your initial state. Whereas half integer spins are actually described by spinners, and so you have to look at your spinor wave function, and when you apply time reversal once, it takes you to an orthogonal state. And then time reversal twice takes you back to your original state, but with a minus sign. So I like to picture this as traveling around the surface of a Mobius strip. So you're back sort of where you started, but you're on the other side of the piece of paper. And it's only once you go around 4 times that you come back to your initial state. And so we say that fermions or half integer spins and bosons or integer spins have distinct behavior under double time reversal symmetry, where half integer spins pick up a minus sign and integer spins don't. And this leads to the fundamental idea of Kramer's theorem, which is that when I have half integer J multiplets, they have to be at least doubly degenerate. And so I end up with Kramer's doublets that are protected by time reversal symmetry. But when I'm looking at integer J ions, these may have non-Kramer's doublets that are not protected by time reversal, but instead by crystal symmetry. However, generically, your non-Kramer's integer J ions are going to have singlet states. So, right, so here is sort of a picture where you can get odd J only doublets, even J you can get doublets. This is the case for cubic symmetry for J equals 4. And these non-Kramer's doublets can be either magnetic or non-magnetic. So the one in cubic symmetry that I mentioned before is a purely quadrupolar doublet and that doesn't have any expectation of J anywhere. And if you look in tetragonal symmetry, you have a Ising magnetic doublet that has a non-zero expectation of Jz, but Jx and Jy are 0. And instead, you actually have quadrupolar. The in-plane components of this doublet are actually corresponding to quadrupolar moments. You can also get non-Kramers doublets in trigonal and hexagonal symmetries, and they behave somewhat similarly to those in tetragonal symmetry. So then we know what effect does this have on the Condo physics. So here's the conventional picture of where you get a Condo coupling. And this is, I start off with a F electron. So here I'm imagining I have Theorem, which has a ground state that's 4F1. And then I have virtual valence fluctuations to the 4F0 state, which here is guaranteed to be a singlet. And this is a generic picture for Kramers doublets because the generic excited state is a singlet. And so these virtual valence fluctuations to a singlet generically give me an antiferromagnetic interaction between the local moment and the conduction electrons that are mediating these valence fluctuations. And so this is the conventional single channel Condo effect, which looks very simple, but of course has a lot of really rich physics in it. And now we can go to the non-Kramers picture. So here I'm going to put one of my non-Kramers doublets as my ground state. And my virtual valence fluctuations are then going to be to some state with an odd number of F electrons. And so this generically has an excited state that is a doublet, not a singlet. And so this is sort of easiest to think about when you think about the quadrupolar doublet, because you're going to again get a antiferromagnetic interaction that's screening the ground state doublet. But here, it's actually going to have two different channels or symmetries of conduction electrons. So this is easy to see in the quadrupolar case, because here the moment of my F electrons is quadrupolar, and the conduction electrons can come and screen that with a quadrupolar moment of their own. But conduction electrons are spin 1/2, for example, and they have, in addition to that quadrupolar moment, a spin moment. And so here tau is representing the quadrupolar moment, and I have conduction electrons that are both spin up and spin down screening that moment, and they're perfectly degenerate at this case. And this picture goes through for the Ising cases as well. It's just a little harder to see. And so you get the two-channel Condo effect, which has very different physics. So if we look at the impurity of this, we can understand really well. If you take the Condo coupling in your two different channels, you can then find that you have a quantum critical point when your two channels are degenerate. When one channel is stronger than the other, you get a heavy Fermi liquid with that particular symmetry. But non-Kramers doublets are always tuned to be exactly in this point. So they're always critical. And this quantum critical point, we can understand it has a 0-point entropy of 1/2 R log 2, which corresponds to 1 Meyer on a fermion. And it has lots of different singular fluctuations in charge, magnetic, and superconducting channels. And so what I'm interested in is what happens when we go to the lattice. So when you go to the lattice, this 1/2 R log 2 entropy has to be quenched. So you can't have the exact same critical state. However, you can do a lot of different things. So you can just form magnetic or quadrupolar order, analogous to the Kramers-Doniak phase diagram. Or you can form a non-Fermi liquid. So this is a lot of what Cox and Zhao were looking at. You can form a composite pair superconductor, which Coleman, Andrei Svelik, and Key, and then myself, Maxime Zero, and Piers Coleman have looked at. Or you can form something that we call hastatic order, which is the analog of a heavy Fermi liquid. And so it's a spinorial hybridization that breaks time reversal symmetry. And this, in other work that people have done, has been, you can call it either a channel symmetry breaking heavy Fermi liquid or a diagonal composite order. So we call it hastatic order, mostly because it's catchier. Hasta is a Latin word for sphere, and it has the same abbreviation as hidden order. But the main point here is that the state cannot form a normal heavy Fermi liquid because that would mean breaking the channel symmetry. So, and then that would take you to this hastatic order state.
Rebecca, can I interrupt you for?
Yeah,
just an elementary question. So in the cubic case, you have all the degrees freedom which are non-magnetic. So spin serves as spin provides the two channels.
Yeah.
Microscopically, so in this tetragonal case, you have one component which is actually magnetic, right, among the three components. And how does the channel index work for that component?
So probably the easiest way to answer this is to tell you to wait a little bit further into the chat or into the talk, and I will show you the microscopic Hamiltonian. But the quick answer is I can see, so I have a doublet ground state, and one channel has a singlet excited state. Two channels has a doublet excited state. And so if you were to add more excited states, that would give you more channels.
But there's still, so in other words, in the cubic case, because the spin degeneracy is robust and so I have a robust channel degeneracy in the two channel Condo way of representing it. So maybe you'll come back to it, but in this tetragonal case, is the channel degeneracy protected by symmetry?
Yes, it's still protected by time reversal symmetry because the excited Kramer's doublet is protected by time reversal symmetry.
Okay, good, thanks.
Okay. So what we're going to focus on is looking at the analog of the heavy Fermi liquid. So we're going to assume that it's going to want to go into some kind of heavy Fermi liquid and not into some more exotic state, like a composite, like a superconductor, or a less exotic state like a magnet. And so in this case, we are looking at the hybridization of essentially our non-Kramer's moments with conduction electrons. So so we can sort of very quickly see the consequences of this as a spinorial hybridization. So here is my local moment ground state. And for convenience, I'm going to represent double time reversal as that 2 pi rotation around my Mobius strip. And so I know that my integer spin goes back to itself under double time reversal. Whereas my conduction electrons are spin 1/2 or some other Kramer's degenerate states. And so these pick up a minus sign when you do double time reversal. And so when I write down my generic hybridization term, this involves a mixing between my local moments and my conduction electrons. And I know how these two states behave under double time reversal. And I know my Hamiltonian has to be invariant under double time reversal. And so this tells me that my hybridization, the mixing term between these two, actually has to break time reversal symmetry and break it like a Kramer's or spinor system. So the hybridization V is actually going to behave like a spinor. So it breaks both single and double time reversal. And essentially it's sort of fairly naive, right? You're mixing spin 1/2 with a spin 1. So of course your hybridization has to carry spin 1/2 in order for spin to be conserved. Okay. So, right. So to sort of get the basic picture of hybridization, I want to go back again to the Kramer's picture and give the very cartoon version of how you develop heavy Fermi liquid behavior. So here we have our local moments, which are our F electrons, and we have our conduction electrons. And as I lower the temperature, these start to hybridize via this V that we were talking about. And we form heavy electrons, which are a mixture of my conduction and F electrons. And you can naturally see that they have a much flatter band, which means that they're heavier. And you develop a hybridization gap that's essentially this mixing between your two types of electrons. So we treat this, so here again, I'm just sticking with the Kramer's picture, which some of you are familiar with. So we treat this using this kind of valence fluctuation picture. And my Kramer's doublet is using this excited singlet state. And so I'm going to represent this with an auxiliary boson B. But in this one channel Condo effect, because this excited singlet carries no quantum numbers, my hybridization doesn't break any symmetry. So this is going to actually develop as a crossover. Theoretically, we describe this single channel Condo effect as the condensation of this auxiliary boson, which ends up reducing the valence from 1 to having some occupation of this excited state. This is sort of within a large N theory, where in the large N theory, this would turn on as a phase transition. but once you include fluctuations, it smooths it out and you get this kind of crossover behavior where your hybridization turns on below some T star. So now we go to our 2-channel case where our excited state is a Kramers doublet. And instead of using a single auxiliary boson, I'm going to use 2, one for each of the 2 excited states. And I'm going to label them up and down. And then I package this together in a spinner, and it transforms like a spinner because this is a pseudo-spin 1/2. And so my excited Kramers doublet is always carrying a magnetic quantum number because it's protected by time reversal symmetry. And that means that my hybridization, as I showed you, is breaking time reversal symmetry as well. And the hybridization is going to develop as a phase transition. And so again, this is described by the condensation of this auxiliary boson, which is now a spinner. And I get some occupation of this excited state. And so a lot of the way we can think about this is as having a tiny moment in this excited state that can then order in some fashion. That's not the entire story. All right, so let's see what we know about this, right? So the hybridization means that the excited state has to be partially occupied. And this excited moment then has to pick a direction in which to quench its entropy. So generically, any of this spinorial hybridization states are going to break time reversal in some form. And exactly how will depend on how the spinner is ordering. But we can sort of pull out some generic statements about these states. So as I said, details will depend on the symmetry that you're starting with and how your spinner is ordering. But it should look like a heavy Fermi liquid. So it should have screened moments, heavy masses, etc. And you should have a hybridization gap that can only develop at a phase transition. And this hybridization gap is large. So it's on the order of the square root of the Condo temperature, which is now your phase transition temperature times the bandwidth. And this state will generically break time reversal. It may be staggered like an antiferromagnet. And this gives us moments. And these are generically small. So these are of order TK over D. So you can get a large gap, but very small moments. And this is sort of the features that were motivating to us about uranium, ruthenium 2 silicon 2, because you can have a large order parameter that's opening up a gap at your Fermi surface and very small moments that are hard to measure because the primary order parameter is harder to measure directly. And the conduction electron G factor should follow your F electron magnetic response. So you expect to get an Ising G factor if you have Ising doublets. If you have non-magnetic doublets, you would expect actually to have non-magnetic conduction electrons at low energies. Okay, and then finally, the heavy electrons are going to have a complex spin structure in momentum space, especially because we have this very strong spin-orbit coupling. So in our 1-channel picture, we have a scalar hybridization that's just mixing these two, and so we get a heavy electron that's a fairly straightforward combination of conduction and F electrons. In our 2-channel case, our hybridization is sort of generically a matrix. I mean, it's really a spinner, but it has more indices, and so you can get much more complicated behavior. And this is somewhat reminiscent of topological insulators. So what I want to talk about now is what's possible with these spinor orders. So first, we talked about this excited state, which has this tiny magnetic moment, which is essentially, if B is representing my excited state, apparently I changed notation, so I'm sorry for that. So B is a 2-component spinor representing my excited state. And I can write down this order parameter, B dagger sigma B. And so this is actually the composite order parameter that has been talked about extensively for these systems. So this is how you write it in the sort of Condo picture, where tau is our channel and sigma is our spin in this case. So this then can essentially depend on the site, and I can order it in different ways. So the most straightforward thing I can do is either make it uniform everywhere. And so in this cartoon of this sort of ferrohastatic state, I'm only hybridizing F with my up electrons. And so I get a heavy up band and then a light down band. Alternately, I can alternate my hybridization between up and down as I go from site to site and get something that is like an anti-ferrohastatic state. And this is a little bit more complicated than the naive picture, so we'll come back to this in a minute. But this excited magnetic moment has the symmetries of a magnetic moment. So it actually has all the symmetries of magnetic order at this point, which is a vectorial order and doesn't have any signatures of the spinorial nature of the hybridization that I put in the title of the slide and the talk. So I obviously really believe is quite important. So that leads to this question of, is this the only order parameter that we can construct that is going to be gauge invariant? And so before I answer that question, I just want to tell you a little bit about this ferrohastatic order. So you get a spin polarized heavy Fermi liquid where, oh, this is shifted. Your down bands is this middle band that doesn't hybridize at all, and your up bands are these two bands that are heavy and have opened up a gap. And so naively, you get a half of a hybridization gap where half of your electrons are heavy and have a gap and half of them are light. And because this has tiny magnetic moments, this is actually favored in field. So we did an analysis where we looked at a competing antiferro quadrupolar order in the cubic case, and you could find a dome of this ferrohastatic heavy Fermi liquid in magnetic field, which is identical to what they've seen essentially in the praseodymium iridium 2 zinc 20 material. And so to sort of summarize the features of this, your spin up and spin down bands have substantially different effective masses. The symmetry is equivalent to a ferromagnet. And in fact, here there are no extra order parameters. And we have tiny moments. They can break additional lattice symmetries. Because it's hybridizing with the, right, it's possible to have some broken tetragonal symmetries as well, or broken cubic symmetries. Right, sorry. So you can have some additional broken symmetries, but they're associated with the order of the moments, and they're not any different than symmetries that you would break in a ferromagnet. That's not a sort of straightforward Ising ferromagnet. But fundamentally, there's no signatures of spinorial origin of the order parameter here. You can really just treat it as a ferromagnetic system if you're looking at a Landau picture. Okay, so now let's go and look at the antiferrohastatic order, which is much more interesting. Because remember, time reversal acts very differently on spins and spinners, and all of our intuition for building magnets is based on spins. So if I want to construct an antiferromagnet, I just I pick two sublattices, and I expect that this is going to obey a time reversal-like symmetry, where if I apply time reversal and then say translate everybody by a lattice site, I get back to my original state. But because if I take my hybridization on sublattice B to be the time reversal of hybridization on sublattice A, and then I apply time reversal to the whole thing, my sublattice B is actually going to go to minus the sublattice A. So it's picking up this extra sign that's really doesn't affect the moment at all, but is a real sign that's there because it is a spinor hybridization. So if I don't have any hopping between my F sites directly, this set can be gauged away. And if I'm in a ferrohastatic state, it can also always be gauged. Any signs that I put on can be gauged away. However, if I have this F electron hopping and I have this two sublattice order, this is going to generically break time reversal. Because if I have hopping of these F electrons between sublattices, I can have a conduction electron come in as a spin up, hop as an F electron, and then leave as a spin down. And so this hopping flips spins and breaks time reversal symmetry. So I can get around this though if I, instead of two sublattices, introduce four sublattices. So I put the time reversal of A, the time reversal squared of A, time reversal cubed of A, and arrange these here in this 1D case as A, B, C, D. So the hybridization pattern looks the same, but here these have a positive sign and these have a negative sign. And so this the moments look the same, but the symmetries that are broken are different. This does not break any time reversal-like symmetry, or not break a time reversal-like symmetry, whereas the 2 sublattice case does. However, in this 4 sublattice case, I no longer have a center of inversion. So this order has broken the inversion symmetry. And you can get more complicated patterns in higher dimensions that break different symmetries. But so these are the 2 fundamental concepts. So this may seem very abstract, but we looked at the cubic phase diagram for, this is the simple phase diagram. And we also put on, in addition to the Condo coupling, the Heisenberg coupling that allows us to treat the F electron hopping as essentially a spin liquid of our F electrons, which are here quadrupolar moments. And we find that we get both ferrohastatic and both kinds of anti-ferrohastatic phases in our cubic system. So these are really there in the mean field phase diagram. And I should just a caveat about this, we didn't look for, you find what you look for. So we only looked for these sort of uniform and staggered moment type phases. Tetragonal symmetry is actually much richer and much more complicated. So the phase diagram for tetragonal symmetry is much uglier. But we have, again, more interesting possibilities. Okay, so let's go and look at these order parameters, right? So I told you the different broken symmetries. So now I want to ask the question of what is possible when I am ordering this spinner, right? So I'll discuss the gauge symmetry of the spinner a little bit later, but what I'm doing is constructing all possible bilinears of the spinner that are invariant under gauge fluctuations. And in the mean field picture that I showed you before, everybody happens. I have a single phase that breaks all of the possible symmetries. But we know that the mean field picture is only valid if I'm looking at, say, SUN spins and not for the SU2 spins that we're actually looking at. So beyond mean field theory, these guys can develop at different temperatures. So this is a sort of schematic phase diagram. So what we can first develop is the amplitude of the excited state spinner. And because this amplitude itself doesn't break any symmetries, it can develop as a crossover above the symmetry breaking transitions. And you can get hybridization gaps from these. Then I can look at the direction of the spinner on the site. This is the composite order parameter that I talked about that behaves exactly like some kind of magnetic order. But what I get now an additional order parameter that comes from intersite interference terms. So it involves this kind of hopping from 2 different sublattices through the F electrons. And this breaks additional symmetry. So this captures the broken time reversal, the broken uniform time reversal in a staggered state, or the broken inversion symmetries. And this is generically complex. So we get this sort of rich possible phase diagram. All right, so now I want to turn to uranium, ruthenium, 2 silicon 2, and talk about how some of this manifests there. So this is a tetragonal system, and we're basing our theory on the non-Cromers doublet, which is Ising-like and protected by a tetragonal symmetry. And the form of this doublet very strongly affects the form of the valence fluctuations. And I'm sorry, I'm missing a little figure here. So there should be a figure for the gamma-6 conduction electrons, which are elongated along the c-axis. So there's 2 different shapes of conduction electrons that can screen the gamma-5 ground state moment. And I can write down the valence fluctuation term by looking at what kind of conduction electron is produced when I annihilate gamma-5 and create this excited state. So I can do this and create a gamma-6 electron, which has this elongated structure, or I can create a gamma-7 conduction electron, which has a squash structure. And this is the exact form of my valence fluctuation Hamiltonian. And so you see the 2 channels are really represented by these 2 terms. Okay, so now we have this picture, and I'm going to go through what we've done to solve this very quickly. We introduce auxiliary bosons to represent the excited states and auxiliary fermions to represent my gamma 5 ground states. And so I can replace these Hubbard operators with combination bilinears of bosons and fermions. And so I get a Hamiltonian that schematically looks like this, where I have conduction electrons hopping. I have an energy of my excited state, which is occupied by my Bs. I have an emergent F electron hopping, which I put in there by hand, although you can also get it if you have a magnetic interaction between your F electrons and decouple that. And then I have hybridization of my F electrons via these two different channels. Okay, so, and so here we can see this emergent gauge symmetry that I talked about. Because B and F are auxiliary bosons, I can always rotate B by this e to the I theta, and as long as I simultaneously rotate F by e to the negative I theta, my hybridization term is invariant. And at the same time, I have to rotate this emergent F electron hopping as well in order to keep the gauge invariant Hamiltonian. And so this tells me that the gauge invariant bilinears of the spinors that I can construct are the amplitude on site, the moment direction on site, and then this combination of this F electron hopping and an intersite moment, essentially. So this is this intersite interference term where the spinor can essentially flip as it goes between different sites. Okay, so in order to actually see all of this rich physics, we had to expand upon the theory that I originally developed with Piers and Fermi, where we looked at conduction electrons that were just S electrons sitting on the uranium sites. In order to actually describe both the case where your excited spinor is pointing in the plane, which turns out to be a pretty good descriptor of the hidden order, and the antiferromagnetic case, where here we're putting the spinor pointing along the c-axis. And so both of these states are magnetic in this excited Cramer's doublet, but they're not equivalent. So this state we could not capture in our original picture. In order to do so, we had to introduce two conduction electron bands. And so we chose to take the two ruthenium sites per unit cell and put a DZ squared orbital on there. We believe that the physics we're getting from this is going to be generic, whereas sort of the S electron band actually was a fairly special case and could not treat this antiferromagnetic state. Okay, so with this model, we could look at the microscopic theory. And here is a sort of one example picture that my student Milan Karniaka produced, where you're tuning the effective hybridization strength, the ratio of the two channels, which you would naively expect to be tuned by pressure or iron doping in uranium on the ruthenium side. And you can get a first order phase transition between the spinor pointing in the plane and the spinor pointing out of the plane. And here, this is this 2 sublattice case, but we can also get 4 sublattice cases as well. Both occur sort of in different places in the phase diagram. So we can reproduce the sort of rough phase diagram of uranium, ruthenium 2, silicon 2 under pressure, where there is a first order phase transition between the hidden order and the antiferromagnet with large F electron moments. And yeah, okay. So, and then the other point I want to mention is that the spinor, we can see that the spinor is very weakly pinned in the plane. So here we fixed it to some particular phi angle, but that's a very weak pinning. So I've identified these two phases as saying this looks like this phase diagram, but there's really no reason you should believe me at this point, because right now, the two orders that we have, if we look at these excited moments, these psi's, I can either have the moments along the c-axis or in the plane. These are moments of my excited moment, and they're quite small. But if we look at the microscopics, and I look at this picture where I have the hybridization spinors pointing along the c-axis, I actually get large F electron moments in this state. So I get large antiferromagnetic moments that are around a half a Bohr magneton, which is what they see in neutron scattering under pressure in uranium, ruthenium, 2 silicon 2. Whereas if instead I look at the static spinor pointing in the plane, I get really tiny moments that are on the order of 0.01 or smaller, depending on what valence I'm using. So that's why I identify this phase as the hidden order, where we get tiny moments or no moments, and the other phase as the antiferromagnet. So then there's the question of, what about the spinorial order? So this is sort of an additional broken symmetry, and we picked, so in uranium, ruthenium, 2 silicon 2, we know the antiferromagnet is staggered along the c-axis with staggered planes that are shown by what these spins are doing here. And then we can pick either the 2 sublattice order that breaks time reversal or the 4 sublattice order that breaks inversion symmetry. And so we can capture all of the order parameters if we sort of look at these two possibilities separately, right? The excited state moment either being along the c-axis or in the plane, and the arrangement of the spinors being either 2 sublattice or 4 sublattice. And these two things are somewhat independent. So if we look at the 2 sublattice order, any 2 sublattice order is going to produce this phi order parameter I talked about, and this gives you a staggered quadrupolar shear type moment. And then if it's coexisting with these guys, you also see that you have the broken time reversal. And so you get a uniform moment in the plane. And then if you have you get a uniform moment that is perpendicular to the staggered moments here for both cases. And then if I look at the 4 sublattice order, this generically breaks inversion symmetry, and all 4 sublattice orders will actually have a uniform dipole moment that's in the plane. Now, of course, these are metallic systems for arbitrary filling, so you won't be able to see the dipole moment directly, but you will see that these are no longer centrosymmetric. And then if I look in the case where I have 4 sublattice order of these two particular spinor directions, I get toroidal dipole moments that are perpendicular to the excited state moments. So these break both time reversal and inversion symmetries, and they're also staggered. So, okay. So these are all that's possible. Now, these additional moments are expected to be actually even smaller than these moments here. These staggered moments I said were already really small because they're suppressed by this order of the F electron hopping over the bandwidth. And we expect the F electron hopping to be on the same order as the Condo temperature. And so sort of at best. And so you're expecting these to be very small. But there are some really sensitive experimental techniques out there, like nonlinear Kerr effects or second harmonic generation experiments that could, in principle, detect really, really tiny moments. And so we propose looking for this. And in fact, Kerr effect measurements have already been done on uranium, ruthenium, 2 silicon 2, and they're suggestive in that you see above the hidden order temperature, which is here at 17.5 Kelvin, you see a tiny uniform magnetic moment essentially turning up in your Kerr measurement and is trainable in field. So this could be analogous to this uniform moment turning on if you had a 2 sublattice order. Now, in our microscopics, the energy between these two particular orders is fairly small. And so it may well be that different samples have different spinor orders. And it may well be that in field you can go from one to the other. That's still a question that we're investigating. But it's possible that you could see these additional orders. Okay. So I want to sort of summarize our picture. So we have experimental signatures, and because the second order parameter phi is suppressed by TF over D, we expect the experimental signatures will be dominated by psi, except for these really small moments. So we can roughly reproduce the phase diagrams of uranium, ruthenium, 2 silicon 2 under pressure and in magnetic field. I think this guy should be rotated. So this is the iron doped sample where you start in the antiferromagnetic phase. and then favor the development of the hidden order, which we also see generically. And then you see that your Ising hybridization is reproduced. That's sort of, we put that in by hand by saying we're hybridizing with our heavy, with our Ising non-Kramers doublet. But actually you have to be really careful because if you have this emergent F electron hopping, you're gonna not necessarily have all Kramers degenerate bands in the end, but you should still expect to see what looks like these anisotropic G factors, even with not all your bands being perfectly degenerate. You expect a hybridization gap to open at T hidden order, which has been seen in ARPES and STM measurements on uranium, ruthenium, G-silicon-2, as well as optical conductivity. And so there's been a lot of other measurements, and one of the most controversial sets has been the question of tetragonal symmetry breaking. And then there's the other question of what about the in-plane moments associated with this XY order. So first I want to just briefly, in one slide, review the tetragonal symmetry breaking picture in uranium, ruthenium, G-silicon-2. So there's a lot of different measurements, and you can sort of classify them into three groups. So one is looking at the lattice. If you're breaking tetragonal symmetry, which you do whenever you order an antiferromagnet in the plane, you expect that you're going to develop an orthorhombic distortion. This was found in one experiment by Yuji Matsuda's group, and several other groups have looked for this and not found it. You can then look at the magnetic response, where via torque magnetometry experiments, also done by Yuji Matsuda's group, they found a chi-xy that turned on at the hidden order. This is the amplitude of this chi-xy. And this suggests, again, that you have broken time reversal symmetry now in your magnetic response, but it was only found in small crystals. So as you go to larger crystals, it was suppressed. And then finally, you have this response essentially of the Fermi surface, the electronic response. And so this is Ian Fisher's group did this elasto-resistivity measurements and found that you get essentially a response that behaves like a two-component order parameter that's breaking your tetragonal symmetry and coupling to a pneumatic order parameter. So this would be compatible with our perpendicular psi in the plane pointing along the 110 direction, which is also consistent with these other two moments. But why is it so hard to sort of pin down the tetragonal symmetry breaking? And there's actually, I have two different answers, which I think are both happening. So the first is, if we look at our microscopic picture, we see that we have large Fermi surface distortions that are breaking tetragonal symmetry. And these are essentially of order 1 because they're of the order of the hybridization gap. Whereas the moments and the in-plane susceptibility are all suppressed by a factor of TK over D, which is around 1/30 for uranium, ruthenium, G-silicon-2. So this should be much smaller. And then the lattice terms are also similarly suppressed by TK over D. And in the microscopics, they're actually tend to be generically a factor of 10 smaller than these magnetic responses. So we do find, tiny quadrupolar moments and small jumps in the elastic coefficients, which have not been seen, and a small orthorhombic distortion, which has been controversially seen. So answer number 1 is there's 3 couplings when you write down the Landau theory. One of your order parameter to the lattice, one of your order parameter to the electrons, and one of your order parameter to the magnetic field, which gives you this torque response. And so you expect this response to be large, and these responses might be very small and hard to see. So if we estimate this, we expect that you wouldn't actually see these jumps in the elastic coefficients. And then to talk about the torque magnetometry, so I told you before that the static moment, if we're looking in the plane, it's pinned very weakly, and we have 4 equivalent minima. And so if we rotate the field as you go around, you expect that for small fields, your moment is sort of going to get stuck in a minima, but eventually it will roll over and try to follow the field. And so you expect this to give you a twofold response. So this is the torque magnetometry data that gives you the chi-xy I showed on the previous slide. And you see above the hidden order, you get only a fourfold response. And then below the hidden order, you get a twofold response. This x-axis, I'm sorry, is missing and should be phi, the angle in the plane. So as I said, for small fields, you expect your order parameter to just follow, to get stuck in these minima. And so you actually expect not a smooth response, but first order jumps in your moment direction and thus the torque as you go around. So here's a calculation we did in our Landau theory, which is based on the microscopics. And this blue curve with the jumps is what you expect in a small field. And if you want to actually reproduce the smooth response that they seem to see in the experiments, you can apply an external Z2 strain, and that then essentially keeps you stuck in one minima at a time as you go around. And so you get this smooth response where you're not jumping between minima. And so this sort of twofold strain is something that you would expect to get naturally at the surface of your samples. And so this is a natural explanation that your small samples have a much larger surface area compared to their volume. And so you're going to get a signal that's dominated by your surface signal. And so you would expect to see this kind of twofold behavior there. And then so that sort of explains why you would see it in small samples. And then when you go to larger fields, you get the fourfold response because your moment and your field are just following one another. So, okay. So this actually leads us to an interesting prediction in that if at small fields and temperatures, the moment is pinned, and at larger fields, the moment is following the field, we actually expect there should be a transition as a function of field in the plane, where you go from one of these directions to the direction of your moment pointing along the field direction. These are all staggered moments. And this is something that would not have been seen before necessarily, because while people have looked in transverse field, if you look at what's happening with your two different order parameters, the x and the y components, you see that the magnitude of the order parameter almost doesn't change as you go through this second order phase transition. And so any kind of scalar quantities like the specific heat should only show really tiny jumps that we estimate are going to be completely within the experimental noise. But if you measure with something that's sensitive to the direction, like elastoresistivity, or we calculated the thermal expansion, you should see jumps or divergences as you cross both of these transitions. Whereas a specific heat would be essentially blind to this transition. So, okay. And I'm running out of time. You should tell me if you want me to stop.
Maybe just a couple of minutes.
Okay, so I just have one more thing to say before we get to the conclusions, which is this question about the XY moments. So the picture predicts XY tiny moments in that plane that are pointing in a particular direction. And you should be able to see this in neutron scattering in principle. And there were 3 different neutron scattering measurements that actually ruled out these moments to the order of 0.0054 magnetons. And then there's the related question of why are the tetragonal symmetry breaking signatures so confusing? And the answer is that you have to think about random strain disorder. So our in-plane moments are very weakly pinned in the plane. And so we can think of them as described by a 3D XY model with a very weak Z4 anisotropy. And so an infinitesimal random strain is known to kill 3D XY order. This is by Imre Ma back in 1975. And so what we have is not quite this. Instead, we have a weak anisotropy, which means that instead of our in-plane fluctuations being completely soft, they have a very small mass. So we have these transverse fluctuations in plane that have a small but finite mass. That means in order to disorder the moments, you need a small but finite random strain. And this is not hard to obtain in uranium, ruthenium, 2 silicon 2 crystals. We know that there's random strain already there. And so it makes sense that you could have in your samples the tiny moments in the plane disordered. And so what's interesting here is that actually hastatic order is more than just in-plane order, right? We're not really just describing the physics of the whole problem with the 3D XY model. Instead, above T hidden order, we don't have any moments, or at least in the mean field picture, we don't have any moments. And at the hidden order temperature, the moments develop and are forced into the plane. And they're also forced to choose their arrangement if they're ferrohastatic or anti-ferrohastatic. And so all of these things will survive. They essentially have large energy barriers between those different states, whereas the energy barriers of moving the moment in the plane are very weak. And so this would be consistent with neutrons not finding the moments because they're not ordered in the plane, but with μSR and NMR measurements that have seen essentially what look like disordered local fields on the order of 10 Gauss, which is on the order of the 0.014 magneton moments that you might expect. And what's additionally interesting is that this mass of the transverse fluctuations can be enhanced. So if we apply a strain or magnetic field in the plane, we can actually enhance the barriers between the different minima. And you can then induce, if your disorder is weak enough, transition into the ordered phase. So this is sort of a generic sketch of a phase diagram where over here in ambient field conditions, the disorder is strong enough to disorder the in-plane order, but you still have a phase transition at the hidden order temperature. But as you increase your field, you start to raise up some of your free energies for some phi angles. And eventually, these barriers go up above your disorder strength. And so it actually picks a direction in the tetragonal. You've broken the tetragonal symmetry by hand, but you're going to see that you've actually developed non-zero moments at this point as well, right? So you're non-zero staggered moments at this point as well. So you're breaking additional symmetries at this transition.
Do you have an estimate about what sort of a strain field you will need for this to happen?
So I don't know the intrinsic disorder strength. So unfortunately, I don't have an estimate. I just am guessing that we're over here, but I don't know how far you have to go to get to this point, and it's probably going to be highly sample dependent.
Mm-hmm. How would you compare that with hydrostat? I mean, with isotropic strain, like the pressure.
So the pressure is going to actually drive a very strong transition between the moment pointing in the plane and the moment pointing out of the plane.
I see.
Yeah.
Presumably this, sorry, go ahead.
I should also mention that as you go through this transition, like the field locking transition I described on the previous slide, this should not show up essentially in the specific heat because your magnitude of your order parameter is not changing. It's just the direction is getting fixed. And so you would expect to maybe see this in elastoresistivity. You would see the fact that there is a transition.
I thought people have done uniaxial pressure experiment on these things, right? Or have people not? Oh. Yeah,
have done pressure or strain? Yeah, people have done pressure and strain.
Yeah, uniaxial strain, in-plane uniaxial strain. Have people seen this induced order, magnet order? Oh.
Not that I'm aware of, no.
I see.
I don't know that people have done elastoresistivity in applied strain. At least I'm not at least not with sufficient, like obviously whenever you do elastoresistivity, you apply some strain. But I don't think it's been done with large strain or in large transverse fields. Okay, so that's essentially the end of my talk. So really the main point is that non-Kramers Condo physics is very different from Kramers physics. And we can get essentially the only example that I know of a spinorial order in a material where you can actually see the signatures of the spinorial order via this additional order parameter. And so I'll stop there and answer any questions that anyone has.
Okay, thank you very much, Rebecca. A nice talk. We have time for some short questions, comments. Andre, you want to start off?
Andre, you're muted.
Sorry. Yes, one is very quick to the phase diagram that's shown right here. At the mean field level, so what I'm trying to figure out is the right-hand side, the pink, yes, where phi.
Okay. Which phase diagram? This one or this one?
No, yeah, this one. Yes, where your mouse is right now, the phase number 3. So at the mean field level, when your slave boson has condensed, the moment you have non-zero value expectation of B, the phases 2 and 3 would be distinguishable in the sense that you always will have expectation value of Bi dagger Bj on different sides if you have one on Bi dagger Bi. Yeah. So what is the physical meaning of the phase 3? Like, what is this off diagonal in real space order mean?
Right, so this is essentially telling you, so when I have a order with spinors, right, I have different signs, say, between my 4 sublattice sites. And that's the only way that an inversion symmetry is broken, is by having the signs of my spinors. So in order to actually see the signs of the spinors, I have to essentially hop through the F electrons. And so this is this interference term that essentially allows the sign of the spinors on 2 different sites to interfere.
So the implication is that even though those spinors might be disordered, meaning that they melted, they no longer have expectation value, they kind of remember the relative sign as you go through the line. Okay. Yeah,
exactly. So it's like a vestigial order where it sort of remembers that it has this relative sign, but it doesn't remember the actual direction it's pointing. Just like a pneumatic order, it remembers its furrow, but it doesn't remember which direction.
Okay, cool.
Yeah, so can I ask
go ahead.
a question? Yeah, so yeah, I'm very interested in this uniaxial pressure induced phase diagram. So where do you expect the anti-Fermi order moment to be? If you
it's still really small.
So I mean, what's the direction of it?
So the direction will be in the plane.
No, I mean, which direction in the plane? Do you have a perpendicular or parallel with the strain direction? That was my question.
It should be parallel with the strain direction. Yeah. So here we put a field, but this is equivalent to putting x squared minus y squared strain on it. And you would get the x squared minus y squared order. So if you did the other way, you would get the other order.
So I mean, so compare with the no uniaxial string, how much more the moment is expected to increase?
Not much, actually. The moment size should be almost unaffected. So it's still going to be on the order of like 0.01 Bohr magnetons or possibly smaller. So it's as hard an experiment as the original one in terms of moment size, but now you'll also have to be in this applied strain. And there's no real guarantee of where the space transition occurs in strain.
Okay. No, I'm just thinking whether one might be possible attempt to try this. Yeah, okay.
Yeah, I think elastoresistivity would be a much easier measurement. So you might try to wait and see if other people can do the elastoresistivity before you would try to do the neutrons.
I have a question, Rebecca, about this pressure-induced anti-ferromagnetic order. So in the description you give, you would, in essence, still hybridization-driven, isn't it?
Yes.
But for practical purposes, is that the same anti-ferromagnet as one would normally get, or there's some distinction in the properties like entropy, etc.?
There's probably some distinctions in principle, so in the mean field picture, there's absolutely distinctions. In that if it's this 2 sublattice order, there's actually like the moment, the excited moment points this way, but the other order parameter points in the plane, and so breaks tetragonal symmetry. So in principle, you would have broken tetragonal symmetry in your antiferromagnetic phase. Which has actually been seen, but that's, I think, independent. of the antiferromagnetic order. That would be small. You would expect to see hybridization gaps still. You would expect to still see this Ising G factor for your conduction electrons. The main thing is that you would have a large F electron moment, a large F2 moment. And so that, of course, would couple strongly to the antiferromagnetic order generated by RKKY coupling or whatnot. And so probably whatever antiferromagnetic order you get would have a mix of mechanisms.
But I'm just wondering, so if I have, say, a vanilla antiferromagnet, say spin density wave, the entropy that's involved in the condensation should track the magnetic order, the amplitude of the magnetic order. Here, it seems like you have this R log 2 or half of R log 2 entropy that would be involved in the condensation regardless of the amplitude of the magnetic order, right?
Yes,
it seems like there's some at least quantitative, but potentially even qualitative distinctions with a genetic spin density wave like antiferromagnetic order.
Yeah, so this still has a large Fermi surface.
Yeah, I can understand that. The Fermi surface hasn't changed. Yeah, but
but it has a large Fermi surface, but it still has F2 moments, which are your ground state moments.
Yeah. I mean, I just also wonder whether the spin waves are the same or not.
I think they will be substantially similar, yes, because essentially the spin waves, they're going to be like spin waves of that Ising moment. Yeah, okay, so what are your actual collective modes that are happening here, right? It's collective modes of your excited moment, which has the same, so I don't know. Okay, so the basic structure of them, the symmetries, the Goldstone modes should behave similarly to an antiferromagnet with that pattern. Because it's coming from the excited moment, the magnitudes of that excited moment is much smaller, and it's anisotropic. So I'm not really sure in the details if it would look similar or different.
Yeah. I think it's interesting. I mean, the broken symmetry as in a spin channel is the same, but maybe things like at least the stiffness versus order parameter, it might be different.
Yeah, that's a good question.
Any other questions, comments? If not, let's thank Rebecca once more. Thanks very much for a nice talk.